Okay, I'm sitting in the parking lot at Urgent Dock while your dad is inside. So I'm going to see if I can make this work. Sitting here, I went through and worked through all of these, and I've got my notes scribbled on this because trying to make notes while I'm sitting in the car is probably not going to work. So we're going to see. All of this is intermolecular forces, solutions, etc. And when you get into solutions and what their properties are, you have to remember that that's always based on whether your solvent is polar or nonpolar, and whether the solute is molecular, so it's not going to dissociate, or if it's an ionic compound that is going to dissociate. I'll get to that later. Okay, so which of the following molecules would exhibit a dipole-dipole intermolecular force? So yes, it has to be a polar molecule. But, so you're looking at molecular geometry, okay? So your nitrogen is obviously not it. You're right to scratch that out because it's a molecular compound. It's two of the same thing. Neither is going to be more electronegative to the other. So it's not going to have, it's going to be nonpolar. The CCl4, while the bonds within that carbon tetrachloride are polar bonds, the molecule itself is tetrahedral. It's nonpolar. So that's not going to be it. The iodine, same thing as the nitrogen, it's a diatomic molecule, it's nonpolar. So yeah, you're left with that that phosphorus trichloride. All of those chlorines are going to be just slightly negative, so that's going to give you that dipole intermolecular force. It's actually a trigonal planar, I think. Actually, it may not be. It may be a trigonal pyramidal, which would give you that polar, the phosphorus sticking up just a little bit. But anyways, they're all, yeah. So, which of the following compounds has the lowest vapor pressure? So, highest intermolecular force gives me the lowest vapor pressure. So, vapor pressure is how much does it want to become a vapor? How quickly does it evaporate? So, a lower vapor pressure, it's not going to evaporate very quickly. Now, all four of these are nonpolars, so you can't look at that. It has to do then with the molar mass. So a higher molar mass, a heavier molecule, is going to have a higher boiling point, which is going to give it a lower vapor pressure. So you just find the one with the highest molar mass, which is going to be the carbon tetraiodide. If I'm remembering right, that's the farthest down the table, so that's going to have the highest mass. I'm checking myself right now because, yeah, that's going to be it. Okay, you got 3 right. Yay, reading from left to right, solid, liquid, gas, yippee, skippy, whatever. Okay, this one. Which alcohol would be the most soluble in a non-polar solvent? Okay, so you want the alcohol that has the most non-polar characteristics to it, which is going to be the one with the longest carbon chain, because that carbon chain is what's non-polar. Okay, the OH that makes it an alcohol is polar. Because remember, which you didn't remember when you drew these, but remember oxygen bends things. So each of these places where you have this OH right here, the H would actually be this direction or this direction. It wouldn't, because remember, oxygen always, here's its electrons and it bends stuff. So the more carbons you have like this, that's more of that molecule that's non-polar, so it's going to be more soluble in a non-polar solvent. Hopefully that made some sort of sense. Okay, this page. Which of the following liquid systems would be expected to have the lowest freezing point at room temperature? Now, this equation that keeps coming up that you keep saying you don't know what these letters mean. So my change in temperature is equal to my K of F Mi. This is the constant for whatever solvent. Okay, and every liquid, every solvent has a K of F. That's an F, by the way. That's not a P. And a K of B. So it's your constant for freezing point and your constant for boiling point. M is your molality, so the concentration of your solution. And then I has to do with how many particles your solute breaks into. If it is a molecular compound or a non-electrolyte, then your I is 1 because it's not going to separate into anything. If it is an electrolyte that splits into 2 pieces, so for instance, potassium iodide separates into potassium and iodide ion, so that'd be a 2. But right here, well, let me go through this. So your M is going to be the same for all of these because they're all a 1 mole solution. So that doesn't change. Your K of F is going to be the same because it's the same solvent all the way through. So that doesn't change. So the only thing that makes this change our freezing point more is the I. Okay. Well, this is basically a non-electrolyte. It doesn't split. So it would have an I of 1. The benzene would have an I of 1. It doesn't split. Sodium chloride is going to separate into sodium iodines and chloride iodines. So it would have an I of 2, but that magnesium nitrate is going to split into a magnesium ion and 2 nitrate ions per unit of magnesium nitrate. So it has an I of 3. So it's going to have a bigger impact on the freezing point. So it's your answer. I don't know why you answer that with a P, by the way. That didn't make any sense, but whatever. Unless that was supposed to be a capital D, which isn't right anyway. Okay. Now, short answer. Which type of crystalline solid each of these are? Nickel is a metal, so it's going to make a metallic crystal. End of story. Okay, carbon. Diamonds. Diamonds aren't molecules. Each carbon is independent of the other. Okay, it's not considered a molecule in itself. So that's our network covalent crystal structure because they are covalently bonded, but each diamond isn't a molecule or a chunk of molecules. It's literally just a chunk of carbon atoms that are covalently bonded. And then this alcohol at the end, the C2H5OH, that's going to be the molecular crystal structure when it freezes. Hold on. Okay. Now, find the molality of a 40% by mass aqueous solution of sulfuric acid for which the density is blah, 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 blah. Okay, you need both of those pieces of information. So I had to do this on a whole nother page because, of course, your scribbles are, I can't follow your math anyways. I never could. Okay. This one. This is an easy solution. It's an easy equation because it's just a proportion. Okay, so concentration and volume of your first one is going to be equal by ratio to your concentration and volume of your second. Okay, their multiple is going to be constant, which made this one like really stupid easy because I have a 15 molar solution and I don't know how much I need to a 3.6 molar in 15 mils. So multiply these together, divide by the 15, you get the same thing. So if you can see my answer down here, hold on, maybe. It's 3.6 milliliters because those two multiply together. But just remember the concentration times my volume is equal to my concentration times my volume. That's easy. Oops, I don't know what I just hit. Okay. Okay, so step 1. Let me make sure I'm in highlighter. So first we have to find the mass of the solution because remember it's 40% by mass. We're given a density, so we can use that to find the mass. So mass is the density times the volume. And we're just going to assume we have 1,000 milliliters. Yippee skippy. So, because, well, it doesn't matter. So here's my density times the volume of 1,000 milliliters because 1 liter is what I need for my molarity. Okay, so here is, I've got 1,305.7 grams of grand total solution. So now I need to know what mass of that is my sulfuric acid. Well, 40% of it. So if here's my total mass times my 40%, then the mass of sulfuric acid is that 522.3 grams. Now I have to convert that to moles. So divide it by its molar mass. So I have 5.325 moles of my hydrogen sulfate, my sulfuric acid. And then to calculate the molarity, I take this, how many moles, divided by a liter. Okay, and I know that I have 1 liter because that's what I used up here. So there's my molarity. So go from density to mass, and then from mass, use the percentage to get the mass of your solute, which in this case is my hydrogen sulfate. Convert that to moles, etc. So you have to have all 4 of those steps. So that was kind of involved. Sorry. So next page. You got this one right. Explain how you would use changes in temperature or pressure to increase the solubility of a gas. Higher pressure, higher solubility, lower temperature. Now, if it was a solid in a liquid, then it would be higher temperature. But for a gas, yes, it's lower temp. So apparently you knew that much. So that's good. Okay. Following 3 compounds have similar molecular weights, so place them in order of increasing boiling point and explain why. Okay, so the greater the strength of the intermolecular forces, the greater the boiling point. Because the more intermolecular forces that have to be broken, then the more energy we have to put in. So that's your boiling point. So the lowest one is going to be the ethane because it's nonpolar. So the intermolecular forces that are there are those London dispersion. They're trying to push things away. That's why alcohols evaporate so quickly. It's the lowest boiling point. Absolutely. Okay. The formaldehyde looks like this, really. I don't know why it's drawing. Like, here's your, well, so here's a hydrogen, and here's a hydrogen. It's semi-polar. So it's going to have, a few hydrogen bonds, but it only has those 2 hydrogens. So it can't form a lot of hydrogen bonds. But now this methanol, which is an alcohol and technically wouldn't, but whatever. It's got, remember, this is going to be bent right there. So it's got 1, 2, 3, 4 hydrogens that are exposed, and then that oxygen makes a corner. So we have more intermolecular forces. We have a lot more hydrogen bonds because we have so many hydrogens. So therefore it has a higher boiling point. Okay, here we go. Here's this equation again. This delta T is my change in temperature, is my K of B this time because I'm dealing with boiling, molality, and then I, that multiplier. Okay, this little statement right here kind of ticks me off because that's just laziness. I'm sorry. A little bit gripey there, but whatever. Okay, so K of B, MI, you could look that up. Can't breathe. So pure ethanol has an initial boiling point of this. What's the boiling point of a solution? If it has 12.7 grams of potassium iodide dissolved in 125 grams of ethanol, is a strong electrolyte. So that means it's going to split into potassium and iodine, so it's got an I of 2. Okay, so is there anything else on that page? I don't remember. No. This page. So here's my thing. There's my I of 2 because it completely dissociates. Molality is moles of solute over kilograms of solvent. So I have this many grams of my solute. I have to find its molar mass, which I found down there. So I have this many moles divided by this many kilograms. So here's my molality, my lowercase m. So my K of B is 1.22. So that times my molality times my 2, because I have a strong electrolyte, it's going to split it into 2 pieces. So that 1.49 is the change in my boiling point. So to find my new boiling point, remember it's boiling point elevation. So I add, it's a positive, I add that to my boiling point to get now 79.5 degrees Celsius. Okay, so boiling point, elevation, freezing point, depression. Okay, this page. This one is a work backward. This, again, here's this make me mad statement. But anyways, so sample of organic compound, so it's a non-electrolyte weighing 1.35 grams, lowered the freezing point by 3.66 degrees. So that's my change in temperature. So non-electrolyte means my I is always 1. Okay. Why is heat of fusion smaller than heat of vaporization? Think of the definitions. Okay, the heat of fusion is how much heat is required to melt a solid without changing the temperature. So my temperature isn't moving right now because remember, if you know, the vapor, the the triple point diagrams of I lost my word, whatever, phase change diagram, you can see where it holds temperature until it's all melted. So how much heat do I have to put in to melt that versus heat of vaporization is how much energy do I have to put in to turn this liquid into a vapor. Well, during which one of those things do I literally have to break the most intermolecular forces? Okay. From freezing from a solid to a liquid, yes, some of those intermolecular forces are going to break, quote unquote, but really they're still in effect. They're just not as tightly formed. But to make it boil, to evaporate it off, I literally have to separate these hydrogen bonds especially. So that's why my vaporization requires more energy, because I've got to break these pseudo bonds to separate this. Okay. Use a drawing to describe what happens when blah, blah, blah. Now, I don't draw. The carbon tetrachloride and iodine, well, those are both non-polar. They don't separate. Okay, there aren't these positive and negative attractions. They don't dissociate. So now I'm working backward. Okay, so 3.66 degrees. I had to look up benzene's KFF. So I'm hoping that either it's somewhere in there or you have it. I had to look it up because that's not something that I would have had memorized. And I wouldn't expect y'all to have that memorized either. Oh, Dad went back. So I guess soon we'll find out what's up. Okay, so, and then there's my molality times 1 because it's a non-electrolyte. Okay, so I divide to get, move my 5.12 and all that. So my molality is 0.715 or 71, whatever I did. Okay, so this is my mass divided by, I'm trying to find my molar mass, divided by my kilograms of my solvent. So is my molality. So this is my molar mass. Hopefully that makes sense. But so when I dissolve an electrolyte in water, remember an electrolyte is going to dissociate. So this potassium nitrate is going to separate into a potassium ion, which is positively charged and therefore will be attracted to the negative, partially negative oxygen end of a water molecule, and these nitrate ions, which are negatively charged and will be attracted to the partially positive hydrogen end of water molecules. So you end up with really, like if this is my potassium and I would have the oxygen end of several water molecules around it, and here would be an NO3, and I would have the oxygen in the I can't speak now. The hydrogen ends around that, so my oxygen is be up here. So that's why it separates. It's like those missiles that we talked about, or I thought we talked about in your class. I don't know. I may not have gotten there. It's all a blur. Okay, hold on. Let me erase this nonsense. Now, the other one that it asks you about, literally just have these carbon tetrachlorides and iodine, they just mix. They don't do anything. Okay, that's as best I can show you what happens. Hopefully all that made sense.